The important words at the top of this page is that with periodic trends, we are not trying to remember them or state them. We are trying to explain them and use them to predict. So when we are explaining, we can't say something as, well, silicon's further to the right than aluminum, therefore this. Or aluminum is higher on the periodic table than gallium, therefore this. That is just stating what the trend itself is. An explanation requires a connection to atomic structure and really bringing in Coulomb's law and attractive and repulsive forces. So for almost all of these, we're thinking about Zeph and we're thinking about shielding. So we're really going to use that claim, evidence, reasoning format. Well, what is the pattern? That's a good thing to know. But what we know about Zeph and shielding are evidence that then allows us to prove or support that pattern. So the first one, and maybe the most important in terms of understanding the rest, also the most important in terms of what's most commonly asked of trends on the periodic table is ionization energy, the energy required to remove an electron. So we would think of that as like sodium plus energy yields, so that's energy, Na plus, this is a mess, plus an electron. So that's super ugly there, but hopefully you get the idea. You could write a reaction to show or to represent ionization energy, or we'll see electron affinity later. It is important to remember energy comes in. We often think about alkali metals wanting to lose their valence electrons, but even for the things that are more likely to lose electrons, energy is still required. It's just a relatively small amount of energy compared to other things. So in the overall process, it becomes favorable. So this sodium's a good example to connect with our row or our period trend. As I go from left to right, so from sodium to magnesium, aluminum, silicon, all the way over to argon, the ionization energy increases. More energy is required to remove that electron. It is harder to remove an electron, and that's because I have more effective nuclear charge going across a row, more protons, while within a single row, I have that same amount of shielding. We are not adding energy levels, so we have the same amount of stuff in between. That means that kind of my Q's, or in Coulomb's law, is increasing. That's a greater attraction because of that Zeph, so that's why they become harder to remove. So when we think about the noble gases as not wanting to lose electrons, it's not because they're full, and that's the full argument. The explanation is they have a very, very high attraction for electrons. They have the highest Zeph. The alkali metals have the lowest Zeph, therefore requiring the least energy to remove them. Within a column, so as I go vertically, the ionization energy decreases. The shielding and distance down a column increases. There's more stuff in between the nucleus and the valence electrons. There's a greater distance there, so our R value increases, while as a result of shielding, our Zeph or our Q's are the same. With the electrons farther from the nucleus, that attraction is decreased, therefore they're easier to remove. The elements closer to the top of the periodic table are less likely to lose the elements electrons than those from the bottom. And you may remember have seen some videos in first year chemistry of lithium to sodium to potassium, rubidium down to cesium. And there's tons of videos out there where we go from very subtle reactions to extremely explosive reactions because of that pattern. When we are talking about the reaction of metals, metals more often than not lose electrons. So ionization energy is the important property that connects to their reactivity. But within this, we can also recognize that these patterns are general patterns that are not always perfect. As I go top to bottom, there aren't major exceptions to this. It always becomes easier because that shielding and distance increases. But as I go left to right, there are a few exceptions. Boron has a slightly smaller ionization energy than beryllium. You could look this up online, or if you went back to the PES graphs, you would see that as well. The last electron is slightly easier to remove. We looked at nitrogen and oxygen and already explained it a little bit as well. The reason here is thinking about not just Zeph and shielding, but connecting what those mean to sublevels and to orbitals. So from beryllium to boron, or really anytime I'm jumping from my S block to my P block, the ionization energy decreases slightly because that P sublevel on average is farther away from the nucleus, making it slightly easier to remove. There's not more shielding necessarily. The Zeph does go up, but that distance or that R value increases. As I go from like N to O, P to S, anything from column 15 to 16, and we would have some similarities in the Ds or Fs as well. We get to that place where we are pairing an electron. So we looked at this and drew this before, but nitrogen has one electron in each of its P sublevels, whereas oxygen pairs in that first. We do have more Zeph, but that additional Zeph with the same shielding is accompanied by extra repulsion. So it does become slightly easier. The greater Zeph is a greater attraction, but the repulsion in that instance is enough that it makes a difference. And ionization energy is kind of unique compared to other properties because we know that an element can lose one electron, but it is also possible to remove a second, third, fourth, or fifth electron as well. Those are called successive ionization energies. An important piece to this is my second ionization energy is always greater than my first. My third is always greater than my second. My fourth is always greater than my third, etc. So we've got that right here. The reason for that is we still have the same amount of Zeph, but fewer electrons. There are fewer electrons repelling one another, kind of pushing each other out. So it becomes harder to take one away. And there is more positive charge per electron. So when we think about that, if I took maybe an aluminum atom, it had 13 protons, 13 electrons, that's a 1-to-1 ratio. But if I take one of those away and I have 13 protons still, but 12 electrons, each one gets slightly more than one proton or slightly more Zeph per electron to pull it a little bit tighter, making it harder to remove. But the important trend here is what I have on the last one. After we have moved the last valence electron, not only does our ionization energy go up, it goes up a lot. And this is a great question that connects to data that you would have to explain, predict, or connect to how many valence electrons does something have. Sodium's got one valence electron. Once it loses it, that sodium ion now only has electrons in level 1 and in level 2. Previous, it was level 1, 2, and 3. So the fact that I only have electrons in 2 levels means the next electron to remove experiences much less shielding. It is significantly closer to the nucleus because now it's in level 2 and instead of level 3. Less shielding means that there's more effective nuclear charge. Less of the nucleus has been blocked. So it becomes much harder to remove. And you would be presented with data often that supports this. And we would see for sodium, it's maybe 500 kilojoules to take away the first electron. The next electron is almost 5,000. For magnesium, taking one electron slightly higher, 700-ish. Taking 2 electrons is about 1,400-ish, about double that. But once you want to get that next electron, so we take 1, 2 valence, to take the third, which is in a lower energy level, we're going from 700, 1,400 up to 7,000 to 8,000. We're talking about 5 to 6 times more energy because much closer, therefore much more attraction. So we definitely want to focus on the trends themselves, but ionization energy is the one where we can see, predict, and explain exceptions slightly more than some of the others, but also understand that this can be and often is a multi-step process that we can explain as well.